Okay. Um, so I just excuse me. What timing? Dang it. Um, I just completed the actual class meeting, and after much of a class meeting had already transpired, I realized that I had forgotten to start recording, and I thought it was better to just do the whole thing at once after class, even though everybody's gone. Um, so I apologize. Um, for the mix-up, and so I've asked students to remind me to please. Uh, I've asked the students to please remind me to record each time. Okay, so what I'm going to do is just go ahead and go through these notes. I'm going to get everything posted on Canvas. So we're starting a new chapter. Chapter 9 is all about numerical differentiation and integration, so performing fundamental calculus um, techniques in using ideas from polynomial interpolation that we saw in chapter 7. So this week is all about numerical differentiation, and then the next couple of weeks or so will be spent on numerical integration. First, I have some announcements. So my office hours this Thursday will be from 1 to 3 p.m. instead of the usual 1 to 4, because one of my PhD students will be presenting her perspectives presentation, pardon me, during the 3 o'clock hour. And then also, for any of you who submit quizzes by including your answers in a separate document, please include the questions as well as your answers. So question, answer in a document. So that way, when I'm grading them, I'm not like having to look back and forth between two things. I don't enjoy grading. I try to get it done as efficiently as possible, while still, of course, fairly inaccurately. So, but including questions, but I'm not, thrown off my rhythm. So I appreciate your cooperation on that. Everyone's cooperation on that. Okay, so numerical differentiation. So the problem that we're trying to solve is this: we're given some function f of x and a point x naught, and our goal is to approximate the derivative of f at x naught, or possibly higher order derivatives such as f double prime. For the most part, I'm going to be focusing on the first derivative, and then I'll get to higher order derivatives toward the end. Now, how you normally compute derivatives is, of course, using all of the differentiation rules that you learned in Calculus 1, power rule, product rule, quotient rule, chain rule. And there are plenty of software packages that implement those kinds of differentiation rules, such as Maple or Mathematica, the symbolic toolbox in MATLAB, which really is just an interface to Maple. But that isn't necessarily the most practical way to use technology to compute derivatives. And here's some reasons why. Um, you might not even have a formula for f of x. If you don't have a formula, um, then all those differentiation rules are useless. You might only have f represented as data points. For example, x-y pairs. Um, Now, what you can do in that case is you could construct a function that fits that data, such as an interpolating polynomial from the last chapter, um, and then take the derivative of that polynomial. And in fact, that is what we'll be doing, as I'll explain to you next class. So that's one thing to think about is you don't always have a actual formula for f of x available. It's just raw data. Second, even when you do have f of x as a formula, software that implements these differentiation rules does not lead to the most efficient way to compute a derivative. It doesn't cater to what computers do best: add, subtract, multiply, divide. If you're going to write a program that will compute derivatives of formulas of functions for you, you have to have some internal representation of f of x that represents all the operations that are performed in evaluating f of x. And so there's storage considerations, allocation of memory, those issues to think about, and all of that adds overhead that can slow things down. And if you have some data structure represents f of x, then you generate from that a similar structure for f prime of x. And just applying the differentiation rules in a straightforward manner leads to a very overly complicated expression for f prime that is not optimized. When we're computing derivatives on paper, we're naturally doing a lot of optimization as we go, just from all of our experience of algebraic manipulations and such. But a computer has to be told explicitly to carry that out. So that complicates matters even further. And optimization is a huge deal. That's an active area of research in computer science because whenever a code of any kind is automatically generated, for example, by carrying out differentiation rules on a function, or just any programming languages that are compiled, like C++. Okay, you write your code, that's just ordinary text, and then a compiler translates that into machine language, and that's what the computer actually executes. And in the early days of programming languages, there's a grave concern, a legitimate concern that whatever code could be generated automatically would not be nearly as efficient as machine language code that would be written by hand and optimized by hand. And the general feeling was that if it was not possible to automatically generate code that was almost as optimal as what could be done by hand, then the whole enterprise of designing programming languages and building compilers for them was not even worth undertaking. Um, but they figured it out. And but it takes a lot of work to try to make code as efficient as possible in an automated way, um, while still ensuring that it is correct. Um, and so that's one issue with automatic differentiation. So the idea behind numerical methods for computing derivatives that we're going to see this week is, yes, we are sacrificing accuracy. We're only computing an approximation of a derivative, but we're going to gain a whole lot of efficiency doing so. And hopefully the error is totally acceptable, but it's quite small. So how do we proceed? The idea is that we have the values of your function f of x at a point x naught at which you want a derivative, and neighboring points, so x naught plus or minus j times h, where h is some spacing between points, and j is an integer. So you can have points to the left or right of x naught. And the idea is that we will um, obtain a polynomial that matches f of x at these points, and then take the derivative of that exactly. So if the thinking here is that if you have a polynomial, a function that's the easiest one to kind of differentiate, if that's a good approximation of f of x, then a derivative of that polynomial should be a good approximation of f prime of x. Now, there are two approaches that we'll see this week for constructing methods for approximating derivatives. The first involves Taylor expansion. That's what I'll do now. And then the second will be using Lagrange polynomials that we saw from the last chapter, and I'll cover that on Thursday. So I'll show you an example. So we're going to approximate f prime of x naught using values of f at these 3 points, x naught plus h, x naught plus 2h. And we also want to quantify the error in that approximation. So what you need to do is take Taylor expansions of f at these points, any points other than x naught itself, and you take the expansion, let me make this clear, around x naught. So x naught is the center of any Taylor expansions that you perform. So that's what we have here, expansions of f of x naught plus h and x naught plus 2h around x naught. And this is what we get. And I've gone out to the h to the fourth term, and actually it's going to turn out to be further than I need to go. I'll be able to give guidance later on how far the Taylor expansion needs to be. Okay. So once I have those Taylor expansions, the form of my approximation is going to be this. So the exact derivative, f prime of x naught, is equal to 1 over h times this expression, which is a linear combination of the values of f at the three specified points with unknown coefficients c0, c1, c2. We're going to solve for these. And then you have some error left over. So that's what we need to find. We need to find these c's and the error. So what I do is I replace f of x naught plus h and f of x naught plus 2h with the Taylor expansions that were computed earlier. All right, so we get this quite a big mess here. And then we group the terms based on order of derivative of f, because we have f of x naught in here, f prime of x naught here, and also f double prime of x naught here and here. So we group by those. So we gather all the f of x naught terms together, all the f prime terms, all the f double prime terms, and so on. So this will lead to equations that will characterize c0, c1, and c2, these unknown coefficients, because I have f prime of x naught by its lonesome on the left side. So that's what I want on the right side also. So, on the right side, I want this term to go away. So in other words, c0 plus c1 plus c2 must be 0. So that's one equation that helps. Sorry about that. That helps determine these coefficients. Next, I have f prime of x naught times something. Well, I want this whole thing to be equal to f prime of x naught. So this expression here, I need that to be equal to 1. So that's my second equation. And then I go to the second derivative term. I don't want f double prime of x naught here because I don't have it on the left side. So this needs to be 0, and that's my third equation. I only have 3 unknowns, c0, c1, c2. So I can only prescribe 3 equations for them that I can solve to get a unique solution for c0, c1, and c2. So I'd like for this to be 0 also, but I can't expect it to be. I can only get 3 equations from getting these to be equal to what I want. So I go ahead and carry out the algebra and solve for c0, c1, and c2. So c0 is minus 3 halves, c1 is minus 1 half, and c1 is equal to 2. Now, as for the error term, now that I have c1 and c2, I substitute them in here, and so that's what I get. Because now, keep in mind, all of this, by solving for c0, c1, and c2 from these equations, everything I've highlighted here will collapse to just f prime of x naught, which cancels with the f prime of x naught over here. So what that means is all of this must be 0. So that's what I have. All of this with c1 and c2 plugged in must equal 0. So now I take this equation and solve it for the error. And once I do, the error turns out to be this. So h squared over 3 times the third derivative of x naught, plus some other terms that have a rate of convergence of h cubed. In other words, they have powers of h that are 3 or higher. Remember, h is meant to be small, so higher powers of h lead to something smaller. So now, after plugging in c0, c1, and c2, this is what I get. F prime of x naught is equal to this. This is my approximation, which is called a finite difference formula. And then this is my error term. Notice it's almost the same as this error term here. The only difference is instead of evaluating f triple prime at x naught, it's evaluated at an unknown point that lies between x naught and x naught plus 2h. In other words, it lies somewhere between the points that were used to obtain the approximation. All right, so this is an example of how we construct a finite difference formula for approximating the derivative at a point x naught. Now, this was just an example. So now I'm going to extrapolate from that to show you how it's carried out in general. So in general, the form of your approximation is f prime of x naught is 1 over h times this summation of unknown coefficients times the value of f at these points xi that are equally spaced points surrounding x naught. So they can have positive or negative subscripts. So each xi is equal to the point of interest, x naught, plus an integer I times your spacing h. The reason for the 1 over h factor out here, it's not essential, but it helps ensure that the coefficients ci are constants independent of h, which is what we saw in the example. Okay, so how do we get to coefficients? So carrying out what I did before, you take your Taylor expansion of each of these f of xi values around x naught. We group these kind of terms together, and so you set the coefficient of f prime of x naught equal to 1, and then you set the coefficients of all other derivatives of f at x naught equal to 0, as many as you can get away with, and you get a system of linear equations. It has this form, matrix A times a vector C equals a vector B. And what are all of these? The vector C is the vector of unknown coefficients from your summation. The vector B has all zeros except for the second element, which is equal to 1. The reason why it's the second element is because it's a second term in a Taylor expansion that has f prime of x naught, what you're trying to get. Okay. Now, what about the matrix? The matrix has these entries. So it's your multiples of h raised to powers based on your Taylor expansion. So where these numbers come from, what I had written here somewhere. Oh, okay. I have that written a little bit later, so I'll explain it then. But for now, I'll just say these come from what's multiplying your derivatives in your Taylor expansions. Okay, now the number of equations in your system is equal to the number of coefficients that you're looking for, and that's equal to k plus j plus 1. So we have a k plus j plus 1 by k plus j plus 1 system of equations to solve. So what you can do, you don't even have to carry out the Taylor expansion like on paper or anything. If all you're looking for is the coefficients, you could just set up a system of equations. You fill in this matrix A and this vector B, and when you solve it in MATLAB, C is equal to A backslash B, which is equivalent to C equals A inverse times B. That solves the system of equations. But this is more efficient than actually computing A inverse and multiplying by B. Okay. Now, that's how you get the coefficients for your approximation. As far as the error formula, that comes from the first terms in your Taylor expansion that don't cancel. And I'll be able to show you a general formula for the error in a little bit. Now, the order of accuracy is the power of h. So the error is big O of h to the k plus j, where k and j are the numbers from this summation that are based on how many points you're using to the left or right of x naught. It is possible sometimes you might get a higher order of accuracy because the symmetry of your points might lead to the error going to 0 faster. And I will be able to show you an example of that shortly. So here's an example, another one. So a 5-point finite difference formula. So I want to approximate f prime of x naught again using using these points x naught and then x naught plus or minus h and x naught plus or minus 2h. So I have a summation going from minus 2 to 2. So I need to find these 5 coefficients ci where I goes from minus 2 to 2. And then I also want to figure out the error. So then I can set up a system of equations and solve it. Okay, here are my coefficients that I'm looking for. Here's the same right-hand side vector that's all zeros except for a 1 in the second position. And then here are my matrix entries. So they are your indices from your summation, minus 2 to 2, raised to powers starting from 0 and up to the number of points you have minus 1. Now, as far as where these numbers come from, if you consider Taylor expansion of f of x naught plus IH, this is what it looks like. You have some derivative of f evaluated x naught over factorial times IH raised to a power. So the I to the k is what's featured in here. I going from minus 2 to 2. So that's how you can get your matrix. So now you can solve a system of equations or have MATLAB do it for you. And then you have the coefficients. So then you have the error formula. Notice that this expression right here in square brackets, it comes from multiplying what would be the next row of a matrix if we had it times this vector. So you're taking here we go up to power an exponent of 4. So now we go to the next exponent of 5, and notice we take these matrix entries and multiply them by the corresponding components of this vector and add them all up. So the idea is we get the coefficients by solving this system, but then we use them down here. And we compute this quantity times the next derivative, the fifth derivative, times h to the fourth. The power of h has to be 1 less because we have this 1 over h factor out here. That causes a cancellation. So all of that plus the error is equal to 0. So in general, the error formula is equal to minus h to the n over n plus 1 factorial, where n, for convenience, is defined to be j plus k. And then you have this summation that has I to the n plus 1 power times your coefficient ci, and all of that's times the n plus first derivative of f evaluated at unknown point. Now, in this example, where we're trying to find a 5-point finite difference formula for first derivative, these are the values that you get. Notice that the coefficient C0 turns out to be 0. And there's a certain symmetry among the remaining coefficients that are negatives of each other. So this is our approximation of a first derivative using, so we call it a 5-point finite difference formula. There's only 4 f values listed in here. It's just because, it's just that the coefficient of f of x naught in this formula happens to be 0, so it doesn't appear. But because 5 points were involved in making the approximation, we call it a 5-point finite difference formula. And then using this formula right here, we get the error term, h to the 4th over 30 times fifth derivative at an unknown point. Now, everything I've shown you so far is for first derivative. Now, what about higher order derivatives? I'll show you an example involving the second derivative. Okay. So, so what we have here is, in general, to get the pth derivative of f at x naught, we have a scaling factor of 1 over h to the p up front, instead of just 1 over h. And then we have the same kind of summation as before, plus some error. And as before, you solve this system of equations. A times c is equal to this vector that I'll call b sub p. The matrix A is the same as before. No change from first derivative. C, same vector as before. The only difference for higher order derivative is that this vector b is different. It has all entries equal to 0, except whatever order derivative you want, that plus 1, that entry is equal to p factorial. So for example, if it was second derivative that you wanted, p would be equal to 2. So the third entry of this right-hand side vector would be equal to 2 factorial, which is 2. And in general, the error formula is the same error formula as before. It's just that this power of h, you have to subtract the order of derivative from it. Okay, otherwise it's exactly the same. So now I'll show you an example of this. For a case of a second derivative, and I'll set j equal to 1, k equal to 1. So the form of our approximation is f double prime of x naught is equal to 1 over h squared times coefficients times f of x naught minus h, f of x naught, and f of x naught plus h, and then we have some error term. So here's our system of equations. So here's a matrix defined as before. So we have minus 1, 0, and 1 raised to powers 0, 1, and 2 times our vector of coefficients. And then our right-hand side vector, all zeros except the third entry is equal to 2 factorial, which is 2. So then we solve this system of equations. And then our coefficients, c naught turns out to be minus 2 over h squared. c1 and c sub minus 1 both turn out to be 1 over h squared. Oh, I'm sorry. I need to back up a bit. The coefficients don't include the over h squared because that's included out here. C0 is minus 2. C1 and C sub minus 1 are both equal to 1. Sorry about that. Okay, what about the error term? So the error, based on the formula I gave earlier, is, so if we go back to this, in this case, P is equal to 2, and N is also equal to 2, because J and K are both equal to 1, N is defined to be J plus K. So we have h to the first power over 2 plus 1, 3 factorial out here. And then we have this summation times third derivative at some unknown point. So then we go ahead and fill in all the particulars. We take all the coefficients, 1, minus 2, and 1, work all this out. But we end up with 0. So that's not the error term. If it works out to be 0, then we need to, this is a case where we're getting higher order accuracy due to symmetry in the points. So the formula is tweaked. Everywhere that in this formula where you had n, it gets replaced with n plus 1. So in other words, actually, throughout we have n plus 1, that now becomes n plus 2. So now this is what we're using. And so we fill in everything, the coefficients that we have, and n and p are both equal to 2. So now we get something that's non-zero in this case. So that is the error term. It's so the error is order of h squared. Okay. Finally, I'll show you an example involving a differential equation. It's a one-dimensional version of what's called Poisson's equation. So minus u double prime is equal to some given function f on a domain x going from 0 to 1. So what we do is, and we're going to oppose boundary conditions on u of x to ensure a unique solution. We're going to prescribe that the value of u at the boundary points 0 and 1 must be 0. So, so what happens is we define a grid of equally spaced points between 0 and 1. We choose a number of grid points, capital N. We define a spacing as such. And then we define our grid points to be integer multiples of the spacing h. I going from, okay, I need to make this clear. So this is for I equal 1 to n. Okay. So then at each one of these grid points, I'm approximating this differential equation by replacing u double prime with a finite difference formula, the one that was derived earlier. So now we have my approximation of u double prime here, and don't forget the minus from a differential equation itself, and that is equal to f. So this left side is an approximation of minus u double prime at xi, and that must be equal to f at xi. So I have these equations for I going from 1 to n. So I put them all together, and I get a system of n linear equations in and unknowns. My unknowns are u1, u2, up to u capital N, that are approximations of u evaluated at x1, x2, up to x capital N. So I'm going to go ahead and solve a system of equations. And then I have my solution is an approximation of u of x, the exact solution of my differential equation, evaluated at all the grid points. So I just want to show you an example of how finite difference formulas are actually applied. So they play a central role in numerical methods for solving differential equations, which is going to be a topic covered in the next course, Math 461, 561. Okay, so I got through all the notes. So if you were not able to attend class live, and all you have is this recording, so do you have any questions about what you saw? Please let me know, and I'll get all the notes posted on Canvas too.